Multi-agent systems involve the interaction of autonomous agents that may be acting independently or in collaboration with each other. Examples of these systems include financial markets, robot soccer matches, and automated warehouses. Today's guest, Peter Stone, is a professor of computer science at UT Austin who specializes in multi-agent systems and robotics. In this episode, we discuss some of the canonical problems of a multi-agent system. And these problems have some overlap with the canonical problems of distributed systems. For example, the problems of coordinating between different agents with varying levels of trust. This resembles the problem of establishing consistency across servers in a database cluster. Peter has recently contributed to the 100-year study of artificial intelligence, so we also had a chance to discuss the opportunities and the roadblocks for AI in the near future. And since Peter teaches computer science at my alma mater, UT Austin, I had to ask him a few questions about the curriculum. To understand how your application is performing, you need visibility into your database. VividCortex provides database monitoring for MySQL, Postgres, Redis, MongoDB, and Amazon Aurora. Database uptime, efficiency, and performance can all be measured using VividCortex. Don't let your database be a black box. Drill down into the metrics of your database with 1-second granularity. Database monitoring allows engineering teams to solve problems faster and ship better code. VividCortex uses patented algorithms to analyze and surface relevant insights so users can be proactive and fix performance problems before customers are impacted. If you have a database that you would like to monitor more closely, check out vividcortex.com/sedaily to learn more. GitHub, DigitalOcean, and Yelp all use VividCortex to understand database performance. At vividcortex.com/sedaily, you can learn more about how VividCortex works. Thanks to VividCortex for being a new sponsor of Software Engineering Daily, and check it out at vividcortex.com/sedaily. Peter Stone is a professor of computer science at the University of Texas at Austin. Peter, welcome to Software Engineering Daily.
Thanks for inviting me.
Your work focuses on multi-agent systems. What is a multi-agent system?
So to define a multi-agent system, first we need to define what's an agent, or an autonomous agent, we say in artificial intelligence. An autonomous agent is a program. It could be a robot. It could be a software program that senses the environment in some way, takes some decisions based on a decision-making process, and then actually executes those actions in its environment in a closed loop, meaning without any person giving input. So, for instance, a robot takes in camera input, decides how to move its motors, and then actually executes it, and then gets new input as a result of that. So that's a single autonomous agent. An example might be an autonomous car. It might be a autonomous bidding agent. Could be a chess playing program that actually has to move the pieces either on a computer screen or in the real world. A multi-agent system is a collection of these autonomous agents. So it could be a group of agents that are either on the same team, or they could be opponents, or they could just be all operating in the same environment. So a group of autonomous cars that are all trying to navigate through an intersection, that's a multi-agent system. Or a team of robot soccer players, each of them controlled by a different process, that's a multi-agent system. And the key is that there's not one program making decisions for all of them, but rather each of them deciding individually what actions to take, trying to maximize some result, either as a team or against an opponent.
And there are collaborative multi-agent systems where the different agents are operating together, and there are also ones where the agents in the system are operating completely independently. Perhaps an independent example might be within trading, and perhaps a collaborative example might be soccer. Can you give some contrast between how the paradigms in the collaborative environment differ from the ones in the completely independent agent environments?
Sure, and I think there's actually a spectrum that goes beyond independent. So there's fully collaborative, on one extreme, and on the other extreme, it's not independent, but rather fully adversarial, where the other agents are actively trying to thwart you. They have the opposite goals as you. So, for instance, in Robot Soccer, you both have teammates who have exactly the same goal as you, and you have adversaries that have the diametrically opposed goal. And then in the middle, there's independent, like either trading agents or traffic, where your goal is to get the car or the trading agent to maximize its own profits or its own minimize its own travel time without much regard for what the impact will be on the others. So I think it's useful to think of that whole spectrum with independent being in the middle. But yeah, to get to your question, it does. The assumptions that can be made in each of these cases are different. So if you're in an adversarial situation, you need to protect against the worst case. In other words, you need to take actions that don't leave any vulnerabilities, because the assumption is that the other agents are going to try to make things as bad for you as possible. Whereas when you're in a collaborative setting, you can perhaps make the assumption that even if they're not necessarily fully competent, the teammates aren't going to be actively trying to thwart you. And so they may have different levels of skill from you, but you don't have to protect against the worst case. You can be more optimistic. And so it's sort of different programming paradigms arise as a result.
Speaking of the actual programming, within these systems, we're often making assumptions like the network communication is low bandwidth, it's unreliable, and in a field like distributed databases, we have well-defined vocabulary for talking about these real-world problems that result from a network, for example. But I imagine that these lead to different problems that are less well-defined if you're talking about something like robot soccer or trading. Are the methods for handling something like a network partition well understood for multi-agent systems?
I mean, that's a good question. I think there are a lot of similarities between sort of networks and multi-agent systems, distributed systems and multi-agent systems. I think it's less precisely defined in multi-agent systems cases, but there are, for instance, there's a body of research within multi-agent systems on coalition formation, for example. What's the best way to partition agents into subteams, or to figure out which other agents you want to form a coalition with for some temporary sub-goal that needs to be solved. And so, I think some of the concepts are similar, but because the sort of the environment or the tasks that agents in multi-agent systems need to address are more sort of open-ended and complex, it's not as clear-cut as in the distributed systems case, how to define the terminology and the various sort of subclasses of problems.
Okay, so let's take an example of robot soccer, which is a multi-agent system, but unlike something that is almost purely digital like trading, in robot soccer you also have the physics of the real world to deal with. So when you have physical variability in terrain, or the joints on the robot that's playing soccer can get too warm, is the handling of those unpredictable circumstances similar to how you would handle something like a network partition in distributed systems, or is it not like that? Is that not the same paradigm?
Well, I'm not an expert in distributed systems, so I can't say from within exactly whether I can't compare the two directly, but my understanding is that it's not exactly the same, and like I said, there's some ideas that can transfer across the various the two subfields, but they're not the kinds of what you specifically brought up in the robot soccer case of joints heating up and that changing the behavior. These tend to be best dealt with at the individual agent level. These are, in multi-agent systems, there's another dimension beyond, whether they're collaborative versus adversarial or independent. There's also whether it's a large system of simple agents or a smaller system of more complex agents. Robot soccer is sort of on the extreme of a small system of complex agents where when you have faults at the level of joints and things like that on a robot, those are best dealt with by the individual agent because it has the computing capacity to do that, as opposed to when you have large systems of much more simple agents. These are sometimes called swarms. Then you have to you have the concepts of redundancy and fallibility and those kinds of things. I think are much more similar to the distributed systems kinds of paradigms.
Where can machine learning be applied to a multi-agent system?
So again, there's both at the individual agent level. There's lots of opportunities for machine learning, but I think that's partly independent of the multi-agent system aspect of it. Then within the multi-agent system itself, some of the classic problems are known as agent modeling or teammate modeling or opponent modeling or sort of the subversions of that, where what an agent needs to do is determine as quickly as possible what are the characteristics of its current teammates. What's a model of how we can predict what actions they'll take as a function of the actions we take. That's sort of one subclass of problems. And then there's just more standard decision-making challenges that come up with individual agents or also agents that are within a multi-agent system, where the agent needs to figure out how best to respond or what actions to take given the models that it's learned in the agent modeling sub-process.
So your PhD thesis specifically covered layered learning in multi-agent systems. Is layered learning the same thing that is referred to as deep learning today?
No, it's actually very different. So layered learning, the concept is that there are many concepts or there are many sort of tasks that an agent or a multi-agent system will need to accomplish that can't be, at least given current methods, can't be learned what's known as end-to-end, where you just take the inputs of the cameras coming into the pixels that come into the camera of a robot and learn a function that goes straight to the joints that the joint angles the legs should move in, but rather you're going to need to break it down into a hierarchy of subtasks and learn each of them individually. So, in the same way that if we're teaching a kid to play a game of chess, for example, we might teach subconcepts such as what's a fork, or how do you castle, or how do you move a pawn, or things like that. Each of these are layers in a layered learning system. And we recently published a paper where we used 19 different layers in a layered learning system in a very complex robot soccer simulation, where some of the layers were things like walking fast or kicking the ball long or standing up and things like that. And they all got sort of patched together. And within layered learning, you can use different machine learning algorithms within each of the layers. Deep learning, on the other hand, it's another word for a complex neural network, which is a particular machine learning algorithm, a particular type of supervised learning algorithm that can have multiple layers. But in contrast to layered learning, it's typically associated with the goal of doing end-to-end learning, where you try to take a very complex process and learn without having the submodules, but learn straight from inputs to outputs. And there are some things these days where that's possible. The premise of layered learning is that there remain tasks or classes of tasks where this end-to-end learning that's possible with deep learning won't be feasible, and then we need to use this more hierarchical subtask decomposition that's used within layered learning.
So your PhD thesis was written in 1998. Can you describe the state of machine learning back in 1998?
Yeah, so that's a ways back. So, but
I'm just curious for the historical perspective.
Yeah, I mean, machine learning is at that point was sort of maybe that was prior to the transition to much more statistical methods, or maybe sort of at the beginning of that transition. There has always, even from before then, there's been sub-communities within machine learning working on sort of Bayesian statistical reasoning working on neural networks that were sort of numerical. But I think that the largest body of work within machine learning at that time, if I remember correctly, was still more symbolic supervised learning methods. And there was also sort of the beginnings of, we were sort of a decade into the sort of revitalization of reinforcement learning, which sort of was reinvigorated at the end of the 80s, beginning of the 90s. And so that was sort of also a fairly small subcommunity within machine learning. And people were really focusing on sort of more and more complex supervised learning methods. And it was, at that time starting to become much more statistical and numeric in nature. And that sort of trend has accelerated and continued to today. There's been, between then and now, there have been various different new algorithms that have sort of come to the forefront. For a while, support vector machines were a very hot algorithm within machine learning. That was after the late 90s, if I remember correctly. That was more in the middle of the 2000s. And then in the most recent past, neural network models have sort of reemerged and jumped to the fore at least for some large class of tasks that people have been working on recently.
Dice helps you easily manage your tech career by offering a wide range of job opportunities and tools to help you advance your career. Visit Dice and support Software Engineering Daily at dice.com/sedaily and check out the new Dice Careers mobile app. This user-friendly app gives you access to new opportunities in new ways. Not only can you browse thousands of tech jobs, but you can now discover what your skills are worth with the Dice Careers Market Value Calculator. If you're wondering what's next, Dice's brand new career pathing tool helps you understand which roles you can transition to based on your job title, location, and skill set. Dice even identifies gaps in your experience and suggests the skills that you'll need to make a switch. Don't just look for a job. Manage your tech career with Dice. Visit the App Store and download the Dice Careers app on Android or iOS. To learn more and support Software Engineering Daily, go to dice.com/sedaily. Thanks to Dice for being a new sponsor of Software Engineering Daily. We really appreciate it. What do you see as the drivers for how those trends change, for why people go from focusing on support vector machines to deep neural nets? Is it that people see a specific breakthrough happen and then they extrapolate in their heads like, oh, this is all the things that something could be done with this particular application, and then that continues until they see the next shiny object? Or maybe you could give me a depiction of how you see those trends being defined from your point of view.
Yeah, I mean, it's a little bit of there's a lot of different factors that go into play. Sometimes it can be a theoretical breakthrough that gets people excited. Sometimes it can be sort of a landmark result where an algorithm that is suddenly able to accomplish something that wasn't possible before. Often when this happens, there is this sort of bandwagon effect that lots of people do jump on a bandwagon and abandon the old methods. In my opinion, sometimes too quickly. And sometimes you get sort of everybody, sort of herding over towards the new shiny object, like you say. I think sometimes it would be wise for the community to keep a more balanced approach and view all of these different algorithms as more tools in the toolbox. They each have strengths and weaknesses, each have situations that they're best for. But it's sort of human nature that when there is a very exciting breakthrough or landmark, that people are become very excited about sort of investigating what its limitations are, and that sort of that often happens. And so it's I think it's probably not only in machine learning or artificial intelligence that this happens, but we have seen it frequently over the years.
When you see the success of deep learning applied to domains that are as human-like or flexible as Go or poker, what are the applications that you think are not going to be ripe for deep learning? Where are the constraints of the problem domain that deep learning is going to be applicable to?
Yeah, that's a good question. I mean, that's part of the reason that there's a lot of sort of frenzy right now within that area of people working on it, is because we don't yet know what the constraints are going to be. There have been sort of a series of sort of surprising successes, and it's not clear when something isn't working, if it's a fundamental limit or if it's just that we haven't tried the right network architecture yet. So there's a lot of incentive to try out new things. So far, what we know about deep learning is that it requires a lot of data, and to really get the most impressive successes requires a lot of data, a lot of computation, and as well as sometimes innovative innovative network structures. The part that we don't know, is what the limitation of the network structures are going to be, and maybe some of the fine tuning aspects of the algorithm. There's still possible room for improvement. I think that there are the biggest limitation that we know of right now is with the requirements for this large data and large computation. And computation always gets cheaper. Data is likely to remain a constraint. And so there's a large class of problems where you want to be able to learn from a small number of examples. If, going back to multi-agent systems, if you're in a situation where you're on a team with another agent and you only get to interact with it for 3 or 4 minutes and you want to improve over that time, you're not going to be getting a lot of data in that kind of a setting. A neural network may not be as appropriate as other possible methods. So I think, that is so far, it's one of the fundamental limitations, is that, you need to be in applications where there's lots of data. And I do think that there's, there are, complex problems that will not, that will remain too difficult for end-to-end learning. But again, that's hard to say. That's not something we can prove. There are certainly problems that are outside the realm of end-to-end learning currently, but we don't know. And with additional advances and additional data and computation, maybe they'll fall too. So it's there's sort of practical limits and there's fundamental limits, and but I do think that it will always remain a very useful tool in the toolbox, and it remains to be seen what's the grand sum of problems that it can be applied to.
It sounds like you have some intuition about where those bounds for what we might be able to do with deep learning lie, but you're not sure where to draw the line or how to phrase it. I mean, would you have seen? Did you feel like Go or poker would have been things that you would have anticipated being tackled by deep learning?
Both are domains that people have been working on for many years, and I've tracked progress in both of them. I've seen very sort of improvements in both from the algorithmic side and from the sort of the data and methodology, training methodology side. I think the Go result was surprising. I mean, there had been progress over the years, and there had been, a year or two before, we had started to see that there were advances both from the planning sort of reinforcement learning side and from the pattern matching side of where the deep learning plays the role, trying to predict what an expert would do. And there were sort of surprisingly competent systems that were using just one method or the other, and so it was inevitable that somebody would try combining them. It wasn't clear when they were combined how successful they would be, or if they would get to the point of being able to beat the world champion. I think I and most people thought that would still be several years away. But it wasn't out of nowhere. There was definitely there have been people working on it, and there have been progress being made. And same thing with poker. That there's it's several years ago there was the group from Alberta had a tournament against human champions at Heads Up Limit Poker, which is much simpler than Heads Up No Limit. They'd been working on extending to the more difficult problem for years, and also had been making improvements. And so, I don't think these were they're a big deal. I think they are landmarks, but they're not. They weren't out of nowhere.
Yeah, I mean, these games have a really big branching factor, but it's still not unfathomable, and we can still define all the branches pretty easily. It seems like there's domains like global economic policy where we wouldn't even know where to begin for how to define all the branches, or like complex medical treatment. But I guess it also remains to be seen, are the humans even doing a good job? Do we even have a good understanding of how to benchmark how well we're doing as, global economic policymakers?
Yeah, I mean, the nice thing about games is that they're very well defined. You either win or you lose. There's, you can get a lot of data. They're in a sort of stylized setting. You can run controlled experiments. There's many other problems that don't, in the real world, that don't have those properties. And, so it's a challenge to even define the problem, let alone learn it.
You're on this panel that's conducting a 100-year study on artificial intelligence. What are the goals of the 100-year study? Yeah,
so actually, I chaired the first study panel within the 100-year study, where we focused for sort of 1 year on writing the first report. My role in the 100-year study is now concluded once we've published that report. The 100-year study, though, is as it sounds, it's a longitudinal study of artificial intelligence to try to, over the years, starting in 2015, well, I mean, it was constituted in 2014, but the first study panel was 2015-16, and the idea is to have study panels constituted every 5 years for at least the next 100 years, snapshotting the state of the art of artificial intelligence, what the progress has been, looking somewhat to the future as to what we would predict the realistic benefits and risks of artificial intelligence are. What are the barriers between where we are now and achieving the benefits, and also what are some of the proactive efforts, the steps that can be taken from a policy perspective and others, public relations perspective, things like this, to maximize the likelihood that the overall impacts of artificial intelligence technologies will be much more beneficial than detrimental. As with any technology, there is potential for positive and negative impacts, and so this, the 100-year study is both both trying to catalog or snapshot over the years where the field is, and also do some sort of introspection as to what steps people in the field can take to help the progress be beneficial for society in general.
People talk about the threats to it being not beneficial. I think on one side of them you have the discussion of automation, and you get to basic income and whatnot, and then on the other side you have the Nick Bostrom, we're afraid that artificial intelligence is going to turn everybody into paperclips because we get an out-of-control paperclip optimizer. And then I think people like Oren Etzioni, who was on the panel with you, I had him on the show, and he seemed to think that this is really not, like the latter, the paperclip optimizer problem is really not something we should be concerned with. I felt he was a little more sympathetic to the concerns of the automation, people getting automated out of jobs, or the Martin Ford type of worries. What are the concerns that you have, and what are the practical constraints or practical measures that we can start to consider around those concerns?
Yeah, well, not surprisingly, as you said, Oren and I were on the panel together, and we share the views on this, that the paperclip optimizer issue is not at least not a near-term horizon concern, and that though that's overblown. Typically, people's views towards artificial intelligence, often fueled by science fiction, the movies and books, are very extreme, either in one direction or the other. Either that the AI technologies will lead to a utopian society, solve all the world's problems, or the opposite, a dystopian society where society is destroyed in some way or another. And in the AI 100 report, we really didn't even give credence to those sort of extreme views. But the issues regarding changes to the workplace, those concerns I do think are very worth paying attention to. It's AI technologies, and again, it's important to recognize artificial intelligence is not one thing. It's not one technology. It's a collection of different technologies, and each will have different impacts over time. But I think, as with many past technologies, these technologies that come out of the field of artificial intelligence will impact the workplace. That is nothing new. There's been lots of technologies in the past that have replaced jobs. There was a time when every time a person placed a phone call to another person, there was an operator, a human operator, that would connect the call with a real wire. And then when the automated switch was invented, that was no longer necessary. That whole class of jobs was destroyed. But it was much more difficult to predict that a company like Cisco and others that make switches would employ so many people in today's economy. And so I think, that's going to repeat with this, with AI technologies. People will be able to envision much more quickly the jobs that will be replaced, but it'll be harder for them to envision the new jobs that will be created. Another, and we say this in the report as well, that most jobs will be transformed or changed in some way before they're replaced. And so, for instance, medical diagnosis software is not in any risk of replacing human doctors in the near term, but doctors are going to need to know how to interact with this software and how to use it to leverage their decision-making capabilities. And same with teachers, and same with many different professions will be transformed, but not replaced. And then the other, I think, important point is that, as with most technology, there's a potential for it to increase the overall wealth of society. And on the surface, that should be a good thing. Production becomes more efficient. Distribution becomes more efficient. In effect, society as a whole becomes wealthier. But we do need to also pay attention to the effect on the gap between the rich and the poor, the haves and the have-nots. And it is possible that some of the technologies, when it's will lead to the concentration of wealth in a smaller number of people's hands if we don't take active steps to prevent that. And so that's something we do address in detail in the report. That it would be wise now to think as a society how we should react to the possibility of these technologies concentrating wealth in fewer people's hands. And historically, when the gap between the rich and the poor becomes too stark, that can lead to revolution. And so to be able to head that off, we need to be able to figure out how to keep a greater degree of equitability within society.
Release the Kraken. Get Kraken, that is. Are you tired of feeling like you're sailing the stormy seas because you have a clunky, old Git user interface? Unleash the beast that is Axosoft's Git Kraken, voted 2017's most popular Git GUI for Windows, Mac, and Linux. Git Kraken is designed to make you a more productive Git user. The app offers efficiency, elegance, and reliability. The UI equips you with a visual understanding of your branching, merging, and commit history, and it features multiple profile support, one-click undo and redo, a built-in merge tool, and fast search. Run the installer, open the app, and set sail with Git Kraken. Easily set up integrations with GitHub, GitHub Enterprise, Bitbucket, and GitLab. That's one high-performance sea monster. Visualize your version control and code on into the sunset, sailors. Visit gitkraken.com/SEDaily and use promo code SEDaily to get $10 off Git Kraken Pro. Gitkraken is free for non-commercial use, so if you're a solo developer, don't worry about the cost. But we'd still love it if you went to gitkraken.com/sedaily. Thanks to Gitkraken for being a new sponsor of Software Engineering Daily. You have some background in music, and there's been significant work done in the area of human-computer interaction for composition. What parts of the composition workflow do you think are ripe for AI assistance?
Yeah, that's a great question, and I actually have a PhD student right now who's working on sort of the whole gamut of musical intelligence tasks, and framing musical intelligence as being sort of a first-class concept. Composition being just one small part of that. I think there are other aspects such as music recommendation. We've looked at the problem of not just recommending individual pieces, but recommending sequences of pieces or playlists, and formulated that as a reinforcement learning problem. We've studied the psychology of music's, or the psychology of people's decision making in the sense of how does the background music that's being played impact the decisions people make while they're listening to that music. And we found some very real effects there in collaboration with a psychologist. So that can lead into composition aspects of having automated processes try to learn how to compose or create music that has desired effects on people, either leading to greater calm or leading to greater efficiency in their work or whatever. There may be opportunities for that. And, there also is the just being able to collate and digest large amounts of past or existing music and being able to sort of generate and summarize, patterns that fit within it. I think, there's exciting possibilities there. Music, the appreciation of music is fundamentally a human concept and very subjective. And so, I think, I'm not going to predict that the act of composition is going to become entirely automated. But I think, like many other things, there will be tools that become useful to human composers, and there already have been over the years, to be able to generate snippets or to complete bases or to come up with new melodies. And so, I think like many other tasks, it's one of these human tasks where there's opportunities for joint collaboration between the human composers and new and improved software tools.
I attended UT as a student, and one of the things that struck me about the UT curriculum is the focus on computer science theory. What do you see as the difference between theory and practice? And the reason I ask this is because as I've done a lot of interviews and spent some time in industry, I've really felt like the dichotomy between theory and practice, it doesn't feel as well defined as the sense I got at UT, but that might have just been my naivete and youth. So what's the difference between theory and practice as you see it?
First of all, the curriculum at UT has changed considerably over the years, and so that we definitely do have we still do emphasize theoretical computer science as one of the cornerstones of a good computer science education, but so is learning about systems and opportunities to do more practical research and within artificial intelligence and other areas as well. But yeah, I mean, I think in all of these areas, in AI included, there are there's opportunities for knowledge gained through theoretical analysis that can help us identify what's possible and what's not possible, and can suggest algorithms that work in ideal conditions. And then there's, aspects that can be, when it comes to trying to solve concrete problems, that can often leverage the theoretical results, or in some cases can suggest new areas for analysis of theory. If there is a surprising result, or if there's a landmark result, such as computers beating the human Go champion, or in poker, these are sort of existence proofs that something is possible that we weren't sure was possible before. And, then that opens up the question of the algorithms that went into it. What are the theoretical limitations of them? And what are the, what can they do and what can't they do? So I think, there's, at least within my research program, there's a close interaction between theory and practice, that the theory suggests what practical problems we should work on. Solutions to practical problems suggest what theory and algorithms we should work on. And, really, a complete research program should really be able to make contact with from both directions.
To wrap up, I know you're an expert in robotics, and we didn't get to talk about that as much as I would have liked to, but can you give us, speaking to a computer science audience, what are the expectations for what you think we're going to see in the next 5 years in robotics, and perhaps the things that we won't see?
Well, I think one of the biggest things coming along, which everybody is sort of finally tuned into now, is autonomous cars, and that is those are robots, and they're probably going to be the most popular robot for quite some time. It's sort of not a coincidence that and the other sort of domestic robot that's made the biggest splash in past years, sort of vacuum cleaners, that kind of niche. These and autonomous cars are essentially need to do navigation, and that's one thing that we've really, the robotics community has made very good progress on, and has gotten to a point of quite good stability. Is being able to sense the local environment well enough to figure out where to move without bumping into things, especially if you have a wheeled robot. So, robots on wheels navigating through spaces, that's something that is technically quite well understood, and we're starting to see applications of that. The other sort of class of applications there is telepresence robots, where they need to move through spaces. What we are, there's still a lot of progress that needs to be made when it comes to manipulation and being able to pick up and manipulate or move around objects in the world. And if and when that happens, that will unlock a whole new, very large class of potential applications. But being able to do that in a robust and affordable way is still something that's being worked on in academic research labs. Is not quite ready for prime time. So
these warehouses, the Amazon warehouses or the Tesla factories that are building cars, these are not, I clearly these are proving grounds for some robotics technology, but it sounds like, I don't have any a good understanding of what the state of the art is that goes on at those places, but it sounds like we're not quite there yet where you can envision a fully automated factory or warehouse.
Well, the Amazon factories, the robots there are doing essentially navigation. They're moving around and moving the shelves around, but at least so far, it's still a person who's picking up the objects out of boxes and putting them into the boxes to send them. So the robots there are doing the navigation. That's the part that can be done, and especially in a controlled environment like a warehouse. But the picking up and manipulation is difficult, at least for unconstrained things. If you're trying to manipulate objects in a very tightly controlled assembly line, then you need you can do exactly the same motion or exactly the same action over and over again. That's also something that can be done by robots and has been done by robots for a long time. But being able to manipulate more dynamically configured objects, just things that happen to be lying around on the table or strewn about on the floor or in a dishwasher or in a laundry basket, things like that. That's still a big technical challenge.
Well, Peter Stone, thank you for coming on Software Engineering Daily. It's been really interesting talking to you.
My pleasure. Thanks for inviting me.
A few quick announcements before we go. Software Engineering Daily is conducting our annual listener survey, which is available on softwareengineeringdaily.com. You can click on the survey link. The survey really helps us understand our listeners and gives us data that we can show to advertisers that help get us better sponsorship deals. Also, the Software Engineering Daily community has started working on MinerRanker. This is an open source newsfeed platform. We are trying to democratize the idea of a newsfeed so that the only news feeds in town are not necessarily Twitter or Facebook or any other centralized news feed. We'd like to make it possible for anybody to make a news feed. So you can check out the MinerRanker project at minerranker.com. You can check out an implementation of MinerRanker at softwaredaily.com. You can find links to all of this stuff at softwareengineeringdaily.com. There you can also find a link to join our Slack group, to follow us on Meetup for future meetups, and other information. So thanks again for listening.